I would like to take this opportunity to introduce X, L, Y, and X, Excellence. Excellence is about how to program the FPGA, and to start, here is a demonstration about programming in general. The source of this page shows the programming of the page. You can see that it looks like a tree structure. Let's look at how the code is written in XML tree programs. Tree editors show the element in their places, and the processor accesses it like using a map, switching its way through. Looking at the FPGA, there is also a tree structure. Unlike the page code, this tree structure is not very readable. The FPGA code is less human readable because people are used to doing things sequentially, one thing at a time, one branch after the next. This approach is fine for the current processors, but not for FPGA, which runs programs in parallel. For the increased complexity of FPGA, one needs to use a different approach, where the codes are considered as boxes in a hierarchy. The schematics show the codes assembled into boxes with inputs and outputs connected together, then wired all at the same time, or clock, in parallel. My first document shows an example where many different parameters are programmed in parallel for wave generation. This requires very fast processing. The example has a very long instruction, CISC, but in implementing this DSP example in the FPGA, we have the same problems that the MIPS guys had with the RISC in the 80s. The instructions need a pipeline. Since the multiplier block and the frequency generating block have different durations, we need to have delays built in, so all functions could be completed within the same time. Here, one sees the different blocks working concurrently and the delay elements that make the functions work in the right moment. In this case, the frequency DDS that needs a few cycles will be all right because of the corresponding delays with the instruction to the gain. This is causing a pipeline-like effect for the MIPS. For parallel processing, programming pipelining can be extremely complex. So the question is, how can we simplify the design entry to manage the complexity of the parallel processes? Here, you can see a visible graphical interface where a state machine inputs and outputs and logics can be defined and simulated to generate the code that is otherwise almost unreadable. Through the interface shown here, it is all visible in one single page. This tool was removed, and it left the sense that to be able to have the design entry exploring the full potential of parallelism, one needed to recreate all the different state or memory and logics. In the 1-bit systolic array ALU document, we look at how to make all the logics and addition, subtraction, multiplication, and division steps. This had been done previously in 1944, but because of the bulky transistors available at the time, they preferred to make things smaller, but slower, and with the MIPS, then had to abandon the multiplication and division because these would cause too many delays. Here, by integrating all in the 1-bit ALU using the NISC, everything can be completed in a single clock cycle, allowing us to preserve the multiplication and division functions. The n-scalable side is really made possible using the 1-bit systolic array to any size and function. Complex functions can also be done in a single clock cycle. The same is true of n-sample sorting. Now, to have the right data in the right place at the right time, the memory handling is described in the last document. We achieve this with the MUX codes. We multiplex the data path, and any memory access is defined by code allowing all the different methods of access. So the idea is to have a big memory divided in concurrent subblocks. Each subblock can be accessed in any way with multiplexers, allowing any programming language to be used. In this document, we analyze how the 4th programming language can be recreated using the MUX codes. The method is actually called TTA, Transport Triggered Architecture. It defines any way that one wants the memory accesses using this method. The method was inspired by the stack architecture of the 4th, but is applicable to any other language. The flexible data path is the key to getting the data any way, in any size, logic unit. NISC ALU. The state machine is then implemented using the memory to store the sequences in the logic. as in this graphical example, corresponding to the way anyone can make a reasonable design entry. We see in the report a small state machine and see one state here implemented in a flip-flop in Logix. In the FPGA, the smaller unit, slice, is actually made up of one lookup table for the logic and flip-flop or storage register that can correspond to one state of a state machine as seen before. The FPGA have up to millions of these slices that can run in parallel. Using this method is optimal because in effect one can have up to 1 million states defined that are like little programs that can run concurrently, like the cogs of a big clockworks. This is also why the 1-bit architecture makes more sense. If we look at the slice, it has 1-bit register and 4 bits logics. So intuitively, we understand that the systolic array of 1944 could open a totally new horizon now, 70 years later, when one has access to the smaller arrays manufacturer, FPGA.